Greetings to all you exquisitely inquisitive ladies, gentlemen, and scholars, and welcome to Physics in the News with Jay Allen, a newly devised method for observing the amazing mysteries of the fundamental constructs of reality has been made possible through the work of physicists from the University of Innsbruck and the Institute for Quantum Optics and Quantum Information, otherwise known as IQOQI, at the Austrian Academy of Sciences. These physicists were the combined forces of two research teams, led by Rainer Blatt and Peter Zeller, and they have just recently achieved the first simulation of a high-energy physics experiment, the creation of pairs of particles and their antiparticles on a quantum computer. As you are perhaps aware, elementary particles are the building blocks of matter, and the properties these particles possess are illustrated within what is called the Standard Model of Particle Physics. A common method of research by physicists in this field is to conduct computer simulations on classical computers, and then will compare the results given by the simulations with actual experimental data. However, the complex and many times counterintuitive nature of the mechanics of elementary particles creates some difficulty when attempting to investigate their nature by use of classical computers. It has been suggested quantum computers may provide a means to accomplish that which classical computers could not. Quantum computers utilize the mechanics of quantum entities that are capable of existing in multiple states at once, encoding information in qubits rather than in the on-off state of classical bits. With qubits, a computer can execute multiple calculations simultaneously and can accomplish endeavors exponentially faster than an ordinary computer can. Although quantum computers are very much in the infancy stage of development, what abilities they have shown thus far seem most promising, as is confirmed true by the work of researchers of IQOQI and University of Innsbruck. Christine Buschik, theoretical physicist of IQOQI, said this about the process, quote, "We have now developed a new concept that allows us to simulate the spontaneous creation of electron-positron pairs out of the vacuum by using a quantum computer," end quote. The quantum system consists of 4 electromagnetically trapped calcium ions that are controlled by laser pulses. And so, experimental physicist of the University of Innsbruck, Esteban Martinez, says that, quote, "Each pair of ions represent a pair of a particle and an antiparticle. We use laser pulses to simulate the electromagnetic field in a vacuum. Then we are able to observe how particle pairs are created by quantum fluctuations from the energy of this field. By looking at the ion's fluorescence, we see whether particles and antiparticles were created. We are able to modify the parameters of the quantum system, which allows us to observe and study the dynamic process of pair creation," end quote. Experimental physicist Rainer Blatt adds, quote, "Moreover, we can study new processes by using quantum simulation. For example, in our experiment, we also investigated particle entanglement produced during pair creation, which is not possible in a particle collider," end quote. The research team of the University of Innsbruck performed a proof of concept for a simulation of a high-energy physics experiment in which energy is converted into matter, creating an electron and its antiparticle, a positron. The team used a type of quantum computer that has shown consistent reliability in the past, that employed a system where an electromagnetic field traps 4 ions in a row, each one encoding a qubit in a vacuum. They manipulated the ions' magnetic alignments. This persuaded the ions to perform logic operations, which are the basic steps in any computer calculation. After a series of 100 steps or so, each lasting a few milliseconds, the team would observe the state of the ions with a digital camera. The 4 ions each represented a location, 2 for particles and 2 for antiparticles, and the orientation of the ion displayed whether or not a particle or an antiparticle had been generated at the location. The predictions of a simplified version of quantum electrodynamics were confirmed by the team's quantum calculations. The stronger the field, the faster we create particles and antiparticles, Martinez says. He and his collaborators described their results on June 22nd in the journal Nature. And so, thanks to the efforts of this brilliant team, humanity gains new strides into the understanding of the fabric of reality. That concludes this episode of Physics in the News. If it pleased you, give it a thumbs up and subscribe for more.